Hello students, we're going to continue with Newton's laws, and in this section we're going to talk about strings and springs. So first about strings. So strings and ropes and chains and that sort of thing always pull. Okay, so that's simple. Now we're going to be doing, of course, we're going to be doing problems, and for these problems we're about to be doing, we're going to ignore the mass of the string itself, or the mass of the rope. Of course, some things like chains are really quite heavy, and it's not very realistic to ignore all of that weight. But anyway, for these problems, we're keeping things simple. So a string pulls. That pull has a name. It's called tension, and it has units of newtons. And in the algebra, we're going to use a symbol like T for tension. And that's going to have a direction. So if we treat it as with direction, it's going to be a vector. So we can often have a vector sign over it. And sometimes you will see F sub t, again T for tension, and of course that can be a vector as well. Okay, now a rope or a string, in order for it to have a tension on it, has to be tied or held at both ends. So tension is always going to involve two objects, one at each end of the rope or string. So in my little diagram here, I'm saying I feel a pull to the right, and then she's pulling on that rope, and she feels a pull to the left. So notice that I've drawn the tension twice. I've drawn it pointing to the left, and I've drawn it pointing to the right. So there's this ambiguity. What do you mean by tension, right? You could mean it one way, or you could mean it the other way. And that ambiguity never gets resolved until kind of at the end, when you're finally plugging in numbers or figuring out how to solve the problem. So to write it to the left or write it to the right, they're both equally legitimate. By the way, this is an example of Newton's third law. So for every action force, like this guy pulling to the left, there is an equal and opposite reaction force. She's pulling to the right. Action and reaction. Okay, now one thing that comes up pretty often is tension problems that involve pulleys. So I'm going to introduce to you a thing that I'm calling the law of pulleys. Of course, that's not an official name. That's a Halverson thing. The law of pulleys. So what it does is that a pulley will change the direction of T, but not the magnitude. So if I have a pulley, let me just draw an example here. Let's say I've got a wheel here, a pulley, and let's say that I've got a rope. I'll draw it in a different color here. Here, this is supposed to be a rope. It goes over the pulley and then down this way. Okay, well, maybe you've got somebody who's down here holding this rope, right? Like here, he's holding it, and he's using that rope and pulley to lift up this box. So he's pulling down on the rope, and the pulley makes a change of direction. Now the rope is pulling up on the box. In the book, they've got another case, which is maybe even more interesting. Instead of pulling, the guy pulling down, in the book they have a picture of a guy pulling at an angle, and there's the tension is this way here and this way here. Okay. Anyhow, that's the law of pulleys. The magnitude of the tension in the rope is not changed, but the direction is. Now, I decided to do a special Halverson example here. This is called a zip line. So these are fun. It's slightly dangerous, but anyway, you have a very strong rope. It's got to be super strong, and it's strung between two buildings or two trees or whatever, and you hang from a pulley, and the pulley zips along from one end to the other end, and so you have okay. So anyhow, the tension, unless you had infinite tension, the rope will not be perfectly straight. It's going to do this kind of V thing, right? Because you're pulling down in the middle with this pulley. And so the tension in this system here, I've drew here a tension for the left part of this scenario. So this is the left part of the rope, and I've drawn it. It's going up to the left and up a little bit, and then also we have the tension over on the right side of the scenario, and it's to the left and down a little bit. So the thing is that the tension on the left side and on the right side are equal in magnitude, even though their direction is a little different. Okay. Now, later on, we're going to want to analyze this problem. And so what I'm saying over here is that it's okay to change the way you think about the tension here. It's okay for you to say, well, okay, the tension is this way on the right-hand side. And you could say, oh, the tension is this way on the left-hand side, although when we come to the problem I'm thinking about, this is not useful. We're going to want to do it where the tension looks like it's pointing up and to the left here and up and to the right on the right-hand side. Okay. So that's sort of getting ahead of us at this point. Yeah, the example problem is in the next section. Okay, so there's going to be a lot more to say about strings and pulleys, but let's move on. Let's now talk about springs. So springs can push, they can pull, and they can do nothing. I've got here an example of a spring. This over here, this represents the wall, a brick wall or something. And the spring, my spring is attached on the left-hand side to the wall, and this dot at the end, that represents the other end of the spring, and this also represents the place where we're going to be measuring X. So right now, the spring is relaxed, and we're going to call that the X equals 0 location. Now, yeah, so it's not doing anything. The spring isn't doing anything, it's relaxed. Now, let's say that we pull on the spring. We pull it to the right. So now X becomes positive. To the right is positive. Okay, well, the spring is going to pull back the other way. That pulling back the other way, so it's pulling to the left, and so my hand is to the right, pulling on the spring, and by Newton's third law, the spring is pulling back the other way. That pulling back the other way is called the restoring force. It's the opposite of the pulling force. And there's a formula for springs called Hooke's law. So here it is, the Hooke's law formula. So the spring's force is equal to minus kx. And x, as we already said, is how far you've pulled it. And k is called the spring constant, and it represents the stiffness of the spring. So if k is a big number, then you have a really tough, stiff spring. And if k is a small number, you have a kind of floppy, easy to pull spring. All right. K has units of newtons per meter, right? So for every meter you pull on it, you get so many newtons per meter. Okay, now this was the pulling case. If you go the other way and you push on it, you push to the left, then x, well, now you're going in the negative direction, and but now the spring is going to be pushing back to the right. So now Hooke's law still gives the right answer, right? Because you're pushing in the negative x direction. X is negative, and two negatives make a positive. So yeah, it works out right. The spring is pushing to the right in the positive direction. Okay. All right, so that's Hooke's law. Now let's have a couple of examples here, a few examples. I have a spring, and I've got a pulley, and the pulley the string goes over the pulley, and it's holding up a mass. And I said the mass is 0.5 kilograms. So the question is, how much is this spring going to be stretching by when you put the 0.5 kilograms? So before you attach this string and the mass and so on, the spring would have been, it would have been, maybe here. And now you've attached the mass, and so now the spring has pulled some amount. And so the question is, how much? Well, the first step to do this problem is to figure out, well, how much of a pull is it? And so you take the mass, 0.5 kilograms, you're multiplying by g, 9.8, and you say, okay, 4.9 newtons. So you're pulling this way with 4.9 newtons. So this is F, pull, 4.9 newtons. And so that means that the spring is now pulling back the other way with an equal and opposite pull. So that's negative 4.9 newtons, right? It's to the left. So we now know the force. We know K. And so the question is, yeah, what's X? And so we're going to say, solve it. X is minus F over K. So it's minus, and then F is negative 4.9. The negatives are going to cancel over 40 newtons per meter. Now, where did the 40 come from? Was that in the previous problems? I'm just wondering. I don't know exactly. Oh, here it is. Okay. The 40 was part of the problem statement up here. I'd missed that. All right, anyhow, you have to know, for this problem, you have to know what K is. So anyway, you divide and you get the answer, 0.1225 meters. All right. And now this problem was set up with a pulley, but it could have been set up this way. You could have had the spring start out, let's say it started out like this, and then you add it, this would be the relaxed position, and then now you hook on the mass, and how much does it move by, how much does it stretch? And it's going to be the same answer. It's just that now X is in the downward direction. And then you could have done it this way. The spring is now holding up. You know, maybe originally it would have, the spring was, let's say, like this, and had like a little platform on it. And then you put the mass on it, and the question is, how much did it compress? How much did it get squished by? And is this going to be the same answer? The 0.1225 meters. Yeah. Okay, one last thing that I want to talk about in this last slide is graphing the spring's force. So, so what we're going to do is make a graph of the restoring force, the spring's force, and so here, this equilibrium position, which is x equals 0, that's x equals 0 here, right? And according to Hooke's law, the force at equilibrium is 0. So this line is at 0. When the spring is compressed, it's pushing to the right, and so you have positive forces here. And when the spring is being stretched, you have negative forces. And the slope of this line is negative k. K, remember, is the spring stiffness. So yeah, there's a lot more to do with springs, and particularly when we get to the chapter on energy. But anyway, this is a little intro to springs. Thank you.